Okay, so good afternoon, or good morning, good evening, wherever you sit to you. I welcome you to this event of the FIW Seminar in International Economics with the title Empirical Productivity Distributions and International Trade. This seminar series is an event as part of the series in Seminars in International Economics, which is organized by our institute, the Vienna Institute for International Economic Studies, in cooperation with the larger funding from the Research Center of International Economics, FIW, you might have heard about and even have already participated in one of the conferences, maybe. The seminar series is basically intended to talk and discuss topics in international economics, to be a forum of presentations for current research findings, focusing mostly on international trade, FDI, and migration. Well, this is highly welcome contributions of today on a very interesting paper. Sorry, my name is Robert Sterer. I'm scientific director at the Vienna Institute for International Economic Studies. I'm substituting today my colleague, Mahdi, who is organizing these events and organizing this seminar series. He's sitting in the train to Prague and we have contact with him, but as the internet connection might be interrupted, so I took over to moderate this seminar, but many thanks to Mahdi in organizing this one. Before starting, let me give some information about the modus and the housekeeping rules. This presentation takes about 30 to 40 minutes and is most often followed by a discussion of about 20 minutes. So you should raise your questions in the chat. And once we know that you have some questions, we can also unmute you and you can or raise your hands and we can also bring you in and you can raise your questions verbally. Well, after the event, we will also send an online survey so that we can further improve the series on all kind of technical aspects and presentations and so on. So we would kindly ask you to participate in that evaluation, because that enables also us to continue with this FIW project and the seminar series in that. Well, as you probably also know and have seen, the event is recorded and we will upload the event on our YouTube channel in the next few days then. Because we get often these questions, the slides of the presentation will not become available because this is still a paper in progress. But once the paper is finished, we will make the final paper or link to the final paper available on the website on the seminar site. Okay, so these are the housekeeping rules and the most important administrative information. Let me come to the topic today. Today's presenter is Katharina Erhardt. She is professor of economics at the Heinrich-Heine-University in Düsseldorf. Prior to that, she had an appointment and as a postdoctoral researcher at MIT and the ETH in Zurich. She completed her PhD some years ago in 2017, I think under supervision of Peter Egger, who is also co-author amongst Sergey Nigai on this paper. So the title of the paper is Empirical Productivity Distributions and International Trade, and we are very much looking forward to the presentation. Thanks for coming.
Thank you very much, Robert, for the nice introduction. Yeah, thank you, everyone, and thank you also to Mahdi for giving me the opportunity to present that paper. I'm very much looking forward to the talk. Okay, so this project aims actually at answering a very or seemingly easy question. What is the role of technology for international trade? Well, you might say, isn't that what Ricardo was all about? And yes, in fact, Ricardo back then, our first trade model that existed, and still the first trade model we typically teach to our students in international trade classes, was all about technology. In the Ricardian world, in the simple Ricardian world, 100% of trade was actually explained by technology. And not only that, it was not only that technology and trade were so densely intertwined in that model, but also in the simplest Ricardian model, technology was captured by one parameter that basically explained everything. So knowing what we see here in the quote, the number, the labor input requirement for producing, let's say, cloth or wine was enough to understand the trade flows in the world. Now, from there, we obviously have moved quite a bit until today. We have, we as trade economists have done some work in the last 200 years, and we reached at some modern trade models that actually do capture quite more reasons for trade and have a quite richer general equilibrium formulation, and yeah, allow for many determinants of international trade. Now, we want to understand today how technology actually plays out in these modern workhorse models of international trade. Now, in today's model, if you think about technology in these modern trade models, in particular our workhorse model, the model or versions of the Melitz model of 2003, there, if you think about technology, we have to look into two different parts. On the one hand, there's this clear Ricardian component still there. So we do have technology that determines where trade flows to some extent. Only in contrast to the Ricardian world, we do not capture it by one parameter only, saying that Austria's productivity in the car sector is X. No, we are now talking about distribution. So we really take into account that there is firm level heterogeneity, that there is different firms that do have different productivity levels. But overall, this whole distribution of firms does matter in determining trade flows. So if a country in one sector has a particularly high number of very productive firms, it will for sure export more in that particular sector. Now, there is, however, a second component of technology in these modern trade models that goes beyond the very traditional technology component of technology in the Ricardian world, which I call technology acting as a mapping. What do I mean by this? To some extent, technology is the backbone of our trade models, because it is not only kind of a shifter that says, okay, some sector or some country is more productive or less productive. No, because the distributions really matter, the distributions of firms really matter in how any policy change, any change in the fundamentals of the model, so for instance, trade policy, how this plays out in this whole model. So by affecting or determining the mass of firms that is actually affected by a given policy change, these distributions in this technology as distribution really does matter a great deal for our understanding of how trade flows emerge in this model. Now, because of this way richer role of technology in these modern workhorse trade models, it is really important to thoughtfully measure technology in order to understand how technology actually impacts international trade, because this is the big question that we want to ask in this paper. Now, before we go to our measurement of technology, let's talk about how we typically do measure technology at the moment in our models of international trade. Well, it turns out in our most specifications of our workhorse trade model, we do use very convenient parametric assumptions. So while we do allow for firm level heterogeneity to play out and really having the micro distribution of the firms matter in the model, we do so by assuming a very, very specific distribution for this firm level distribution. And in particular, we do not kind of micro-bound this distribution, but we take very convenient assumptions that actually lead to the fact that by assuming ex ante in this case, Pareto distribution for the firm level distribution, that leads to a macro formulation of trade flows that can then be used to actually calibrate these micro distribution without ever looking at the micro. So I think this is very important. It's not only that we use parametric assumptions, but we use them without actually looking at the microdata, but we choose ex ante a model that leads to a macro outcome that allows us under this assumption to estimate the distribution of that model. And yeah, use that to parameterize the micro that we've actually never looked at necessarily. So there's no validation of aligning to firm level data. And this has now important consequences, in particular for us, as we are interested in understanding the role of technology for international trade, because we will very likely mismeasure the role of technology for international trade if we constrain it ex ante before ever looking at the micro level to this very specific and very constrained, because it's only one parameter that's allowed to vary, to this very constrained version of technology. And secondly, which is also very important, it's not only that technology, as I said, is not only a shifter in this model, it's also really the backbone of the whole model. So whenever we assume a certain distribution, it does not only affect that a effect might be a bit larger or a bit smaller and like something like that. No, it really matters qualitatively, because it really determines where and how the effects play out in this whole world. So it is really important. And a third consequence that I don't want to talk too much about today is the misperception of the isomorphism of very distinct trade models. Now, I want to convince you that this mismeasurement actually really matters, and that it does matter more than typically assumptions do matter in economic models. Because I do see that some people might say, like, okay, isn't that a bit cheap? Like every model makes assumptions. That's kind of the core idea of a model to start with. So clearly we also make parametric assumptions for a trade model. So that should be fine, no? Because like, assumptions is just a bit more and a bit less. I want to argue that actually it does very much matter in this particular context. And I think it's fair to ask the question in our context, because first of all, we do want to understand the role of technology for international trade. So it's important to really measure it the right way. But secondly, what is also very important is, and this I want to kind of demonstrate here in a super, super easy way, it does matter more than we might think. And already in a very, very, very simple model of 2 countries only, 2 sectors only. And that's what I want to illustrate to you now. Before I really go to our data, let's start about very, very easy ways of how we could model this technology in our trade models. And here I portray 3 ways of how we can vary the distribution of firm level heterogeneity. One way one could think about how distributions of firm level heterogeneity vary across countries might be location. So we could think about, okay, one country might have a productivity distribution of firms that lies here, and the other country might have a distribution that lies here. So we can basically shift the whole distribution to the right by making everyone the same way more productive. Another thing what we could do, or another way how the distributions could vary, or what one could think about, is the scale, meaning that we put more math in the middle. So there's kind of a country where a lot of firms do have a similar productivity level, and then there's very, very few firms that are in the tails of the distribution. That's another easy way how we could imagine that distributions vary across countries. There might be one country where there's more so-called medium-sized enterprises, while other countries might have a higher dispersion here. Then a final very easy way of how we could think about the distributions to vary is the shape, where it's really now an asymmetric way of varying the distributions by simply putting more or less weight into the left versus the right tail. Now, these 3 very, very standard and very obvious ways of how distributions might vary across countries do already matter a lot in the simplest version of our trade model. So if we consider a very simple Melitz model with 2 symmetric countries, completely symmetric in terms of size and everything, we have one sector only, no input-output linkages. So really the easiest way we could model our workhorse trade model. And we want to check out if these very, very easy and straightforward ways of how distributions might vary in this model, how they already matter qualitatively and quantitatively in that part. Throughout my talk, so here in our toy model and also later on in the real model with the real data, we want to look at two versions of the role of technology for international trade. One, going back to the recording question. So what is actually really the technology, what we call now first order effect of technology in trade? So how does technology actually impact to which country we export or from which country we import? How does it shape the pattern of trade flows that we observe in the world? So that's what we call the first order effect of technology and trade. That basically asks, where is actually Ricardo in the Melitz model? The second question that we want to ask is regards the second point that I emphasized before, that technology actually is not only determining this recording component in our modern trade models, but it's also the backbone of our models. So every effect in our model is governed by technology. How everything that we think about in our model plays out will be affected by technology and trade. So that's why we also want to look at the so-called gradient effect of technology and trade. So we want to understand if we change something, the fundamental in the model, and we will use trade costs, because trade policy is what we are typically interested in as trade economists. We want to understand how this affects how technology interacts with changes in trade costs in these different versions. Now, what I want to illustrate here is that already these three very, very easy variations and very straightforward, obvious variations of distributions across countries, which we could easily believe exist in the world, do matter dramatically in this easy model. So for instance, consider the first case where we change this location of the importing country, so country J in this case. So meaning that we do here an experiment where as we go from here, from the origin to the right, we do change the location of the importing country, the J country, the more and more and more. So we move it to the right. So it becomes more and more productive, the whole distribution moving to the right. Well, what happens? Clearly, it will export more to I, while I will trade or export less to J. So this is a kind of very straightforward way. If we now do a different change in the distributions, so instead of moving the location, moving J's distribution to the right, instead we leave it where it was. But now if we change the shape, we see that as we move to the right, so here we are now in this, if we move, okay, let's stick to the order here. Like, let's first move the scale. If we move the scale first, so meaning that we put now, as we move forward, putting more mass in the middle, taking out mass from the tails, we are in the red case, then as we do that, this has way larger effects compared to shifting the whole distribution. So this really matters a lot, already indicating that different changes in technology have very different effects in that model. So here we see that has a huge effect on trade flows as we move from the left to the right. And the third version that we look at, that's the black one here, that's the shape variation, where we put more mass from the right to the left tail. And as we do that, the changes are relatively minor compared to the big changes here in red, which were the changes here in scale. Now, already for the first order effect of technology on trade, what we can state here, in the easiest version of our workhorse trade model, it matters a lot of how we specify technology in that model, beyond our standard treatment, where we would only allow one parameter to vary. So here we have already three parameters to vary. 3 parameters matter already a lot, but obviously in reality we could think about millions of parameters more that might vary, and exactly that's what we want to do later on. We want to consider non-parametric distributions and really move all possible parts of the distribution and understand how they impact trade flows.
Let me quickly take the privilege of being the moderator, just to be sure. In the simulations, say when you change the scale or the shape, then you keep the average productivity constant. So it's only really the shape which is changing, not implicitly also the level of productivity is changing. In
those simulations or later on?
In these ones.
Yeah, in these ones we always go back. So we always start again from the same benchmark and then only change one dimension of the scale. Yeah, so here we change location, but by changing the location, obviously we also change the average productivity because we move everyone to the right. But then we start here again, when we look at the red case, we kind of start again from symmetric distribution. So here it's a symmetric case where both countries have the perfectly identical distributions. And then we move the J country away from the distribution of I in any of those 3 dimensions that I considered.
Okay, maybe I come back to that later.
Yeah, but I think it's an important question, and it will lead, and was a big discussion of us actually in this paper, and I'll talk about it later when we talk about our simulations, what we didn't actually do, because we will not change any of those dimensions because we have a non-parametric distributions. What we will later do is we want to try to change the distributions across sectors in a way that we keep the average as it used to be in the benchmark, but eliminating differences across sectors, which is exactly what comparative advantage is. Perhaps that's kind of goes in the direction, but let's talk about that when I talk about our experiment in our case. Okay, so and here the same thing. We see that not only the first order effect of technology on trade matters a lot in these 3 different dimensions of how technology might vary, but also the so-called gradient effect. So if we change trade costs in these models, so here we look at a given change in trade costs, so 20% reduce trade costs by 20%, and we look how this 20% trade cost reduction plays out in the model in terms of how it affects trade flows, and we see that a given change in trade policy does have very different effects depending on how the technology of country J is specified. So if you want to use our models and understand how changes in policy, for instance, matter in these models, it's again very, very important to get the distributions right, because the distributions are the backbone of our model, and the distributions do determine how any changes in fundamentals play out in the outset. Now, this paper is now actually, and that's why I've illustrated this in this toy model, basically. Our paper is exactly, we want to do these toy models here, but going a step further, not taking 3 parameters and 4 parameters, as some people might use. Now, really want to go to the really micro. We want to have a really nice, with not completely unconstrained version of the microstructure, by using non-parametric representations of firm level heterogeneities across countries and sectors, and putting those into our standard full macro general equilibrium model, without like really the standard one with input output linkages and everything you might be interested in, not making any compromises there, but feeding it with the true distributions, the non-parametric distributions, instead of the parametric ones, and see out how that matters. And once we have done this, once we have this model, we will use that as a laboratory to actually understand the question we started this project with, is what is actually the role of technology in our modern trade models, in contrast to a Ricardi model, where we as a field started with, where trade explained was completely to 100% explained by technology. We want to understand how is actually now in our modern trade models, where we have incorporated so many more channels, how does technology and trade interact in these modern trade models? And secondly, we also want to understand this gradient effect. So we want to understand how does actually qualitatively, how do our responses, the qualitative responses in our trade model interact with the choice of technology. Now, very importantly, and that's I think quite nice, that in contrast, because we do not really observe changes in technology in the world that we could compare and benchmark our model with, but the gradient effect of technology and trade gives us actually an opportunity to confirm predictions that come from our correctly specified model and look how well it fits some observation that we actually see in the data, and align it with these data in a way that our traditional way of specifying the model would not allow for. Now, this sounds kind of good, so let's start. And that's kind of where we started some years ago. Now we wanted to start, but it turns out, well, there's one more challenge in this whole thing, and it's measuring this firm level heterogeneity turns out to be really, really, really hard. And yeah, that's actually what we've worked quite a lot on in the last year, and tried to come up with a solution, because the problem was in our original version, we tried to use standard methods from empirical IO, where there's a lot of new ways to estimate firm level relativities, and we wanted to employ those methods in our context. The problem is that the state-of-the-art methods that exist to estimate firm level relativities rely on very, very detailed data, and these kind of data are actually infeasible to get for a large set of countries. And we, for our question to be asked, need a large set of countries and sectors to get these distributions for. But even beyond data availability, there are still important challenges if we use those methods, because they are not necessarily the assumptions needed for identification in this model are often inconsistent with certain assumptions in our workhorse trait model. And we want it to be super consistent, both in estimation and in the model itself. So that's why we started to think very deeply and we want to now propose a novel methodology that allows us to recover the empirical productivity distributions from aggregate sales data alone of individual firms and use this aggregate sales data to, in a consistent way with our trait model employed, and get really at these baseline underlying empirical productivity distributions from the aggregate sales data using the model and having a theory consistent way of getting at this productivity distributions. And I will talk a bit more about this later. And the nice thing about it is, first of all, it's fully consistent with the trait model employed. Secondly, data on aggregate sales are widely available and also well measured. And relatedly, we do not need to measure quantities, which is typically needed in the standard empirical methods from IO to estimate firm level productivities, and hard to get it for individual firms. Now, with this, we are finally ready to make this paper. And I think with this paper, at the end, we have quite some nice contributions, because first of all, we are then able to answer the questions that we asked in the very beginning, so actually quantify the role of technology for international trade, using these true empirical underlying productivity distributions. Also, I think from the, what we see and what we can illustrate using these empirical productivity distributions as the backbone of the models, we can really illustrate how important the micro mechanisms that are governed by these distributions are in our models, not only for the micro itself, so to understand if it's like 5 or 6 firms that are exponent. No, it's really important to understand the macro outcomes of our models. So for instance, as we see that we will get at non-constant trait elasticity, something that we clearly observe also in the data. Apart from that, I think we also have some methodological contributions. So first of all, we employ novel quantitative algorithms that actually allow us to accommodate this, our workhorse trait model with arbitrary non-parametric productivity distributions, which is substantially harder compared to simply using a very convenient parametric version of these distributions. Secondly, this novel algorithm to actually infer model consistent productivity distributions from microdata on aggregate sales. And third, I won't talk too much about this today, but we also propose a new mechanism using inverse propensity weighted non-parametric density estimation to obtain really representative microdata to use and really get representative distributions to be used in our laboratory later on. Okay, I do not want to talk too much about the literature, but go right into the model. Most of you will know the model I'm talking about because it's the workhorse trait model, but so everyone is on the same page, let us quickly go through the main assumptions that we are taking here. So we're working with a multi-country, multi-sector version of a monopolistic competition model a la Melitz, meaning that we have a final demand across several sectors where we have a Cobb-Douglas version here with final consumption shares being fixed for each sector. Then every sector consists of the CS aggregate of goods available for consumption. On the production side, firms use both labor and intermediate inputs. So we have these input-output linkages in the model, and they vary, each firm varies by relativity. And so by this, clearly the costs of production for each firm depend on the wage rate and the cost of intermediates in a particular country and a sector. Now we fix the number of potential producers in a given firm to not allow for any corner solutions, and these fixed numbers of potential producers draw the productivity from a distribution. And importantly, it's a distribution, so we do not specify this distribution ex ante. Trade is subject to trade costs, so we have, and this together with monopolistic competition gives us this classic constant markup pricing that we're well familiar with in our trade model. So we have this constant markup over marginal cost here, defined by sigma, our elasticity of substitution. We have the marginal cost of production, productivity, and here our trade costs. Apart from iceberg type trade costs, we also have fixed cost of exporting, this FIJF, and those lead to a zero profit condition that determine the margin exporter. So the important concept in the Melitz model is that not every firm does export, but only the most productive firms do export. So this is the zero profit condition. Well, taking all this together, we at some point can specify our trade flows or trade shares from one country I to another country J, which depends on many of these parameters, and in particular here, and this is the core of our model here on these distributions here, depends on the fact how these phi's are distributed in a given economy, which then of course also interacts with this endogenous cutoff productivity here that determines which part of the distribution we actually have to look at to understand the exports of a particular country to the other one. Now, to close the model, we have to understand that total expenditure is the sum of final demand by both consumers and intermediate demand by firms. And then, assuming balanced trade, very classic, we close the model. Now, as I already said, what is really, really hard is actually measuring technology in a consistent way. And we aim at obtaining representative empirical productivity distributions for 15 countries and 17 manufacturing sectors. Our main data source will be balance sheet data from the Orbis database, where we actually get these aggregate sales data from that we will mainly use. But we need also some additional data. So we need sector country level firm size distributions, which we use for the inverse propensity weighted kernel density estimation, so that we really get at representative distributions. We need the share of exporting firms by country and sector. This we need for our new methodology. And now I want to give you a short overview, a short sketch of the idea of how we actually get at these distributions from aggregate sales data. Here's a small idea of how our data look like. So we have here the 17 sectors. These are the WIiw sectors you probably are all or many of you are familiar with. And the countries we have are actually quite nice. It's many European countries, but we also have countries like China and Korea, and also within the European countries, some quite nice heterogeneity, kind of having Romania and Bulgaria, as well as Germany and France. Like we really have very different kinds of countries, which is then really nice to look at the distributions and see how they differ across different countries, but also across different sectors. Now, how do we, so I wanted to not talk about the representative part here. We can talk about this later on if you're interested in that. What I want to talk about is how we actually recover productivities, because this, I think, is a quite nice way of getting at this data. Now, the intuition is super simple, and it has been used by others before, in particular by Arkoulakis in his work with French firm data, where actually there is information on domestic sales. And if you have information on domestic sales and you assume that all firms that do export are also active domestically, then in the context of a Melitz model, this is enough to actually place all the firms relative to each other, because the only thing that does vary on the domestic side is then only the firm level productivity of each firm. So if you do have domestic sales of these firms, you actually can rank them towards each other, but also understand how they are positioned in productivity relative to each other because of this, because only the distribution of, or only the productivity of each firm varies to determine these domestic trade flows. Now, this is nice. So we could, if we would have domestic sales, we're actually quite one step further. The problem is we do not have domestic sales, at least for most countries. So we need to trying to get at domestic sales somehow. Now, our idea is to recover the domestic sales step by step using the model at hand. So the intuition is as follows. just as for the domestic sales, and as the domestic sales give us a relative ranking of all the firms in an economy, and this is true for a subset of firms that exports to the same set of countries. So take the most difficult market, where the most difficult market is defined by the market where the smallest share of firms exports to. Well, for that small share of exporters, we actually can exactly do what we can do for domestic sales. For that small set of exporters, we can actually rank them accordingly and get their relative productivities via each other. Now, once we have that, we actually do know total sales to that country, to that most difficult market. Now, and given that we do know that, and we do know how the individual sales have to be distributed across those firms, because we do know for that subset of firms how they are positioned relative to each other, we can actually distribute those total sales to that most difficult market across these firms and take these sales out from their aggregate sales. So now we have for that set of firms, not their total sales, but we already have their total sales, but the sales to the most difficult market. That means that now we do have some information about a larger set of firms already. We can now look at a large set of firms and their sales to all markets, but the most difficult market. And we can do exactly the same. Again, we can now, for this set of firms that's a bit larger than the old one, we again can rank them accordingly, understand their relative productivities to each other, again, distribute sales across these firms, take them out, and so on, and so on, and so on, until we get at the end to in a theory consistent way to the domestic sales of these firms, the distribution of domestic sales of these firms, which then allows us to understand the firm country sector level distributions of these firms up to a constant. This is important. We will know it up to a constant because we have then normalized these distributions by the most productive firm in a given country. Now, in the last step, what we have to do then is we use aggregate trade data to then position the country sector distributions relative to each other. So let me show this here. So here we see the intuition that I just said. So this is the total sales of a given firm with productivity phi. This is how they look like. You see that the only thing that varies at the firm level is this phi to the power of sigma minus 1. Given that this is the same for all the firms that export to the most important, to the toughest market, we can kind of, by putting them relative to each other, we get rid of this term and we get this relative distribution of these firms. And we do this step by step until we get at some point to this distribution of this so-called phi tilde, which is related to our true distribution by with this phi bar. Now, what I want to talk about now is how to get at this phi bar. Now, this phi bar we can get at because now we actually already do have all the information on the firm level that we need, and that's actually something we can really get from macro data, because if we do specify our trade shares in this Melitz world, we do see that domestic trade shares here will depend on a lot of things that we do know from data, plus this phi tilde and how it's distributed, which we already do know, and this constant here. The only thing that we do not right away know in this equation here is the price index. But the price index we can actually recover by using data on price levels in countries and sectors, and with some derivations, we can use that to recover price indices. Once we have the price index, we have information on all these things here, but this, and we can recover these phi bars that now allows us to kind of position all these distributions relative to each other. Now, once we do that, and if we do that, this is what we get. We get this very nice set of many distributions. We will have estimated 255 productivity distributions across the world and sectors. You cannot read too much out of this, so let me kind of zoom in a bit and take a look at particular sectors. So here we see the productivity distributions for the manufacture of textiles, where we see that the countries are relatively close to each other, while they are substantially more diverse when it comes to something like perhaps more involved or more advanced sector like electrical equipment, where we already see that there is quite some ranking and also clustering of certain countries. It's actually a kind of a hobby of mine to look at these distributions, because I'm always quite fascinating how well they fit many of the ex ante assumptions one might have had on how these distributions rank to each other. Now, you might be interested in how actually these distributions vary across countries and sectors. So does every sector in a given country have a quite similar distributions, or where is the bigger variation? So we do see that actually there's a lot of variation. I mean, that's what we see here. These distributions are very, very different. We do see here, we look at Kolmogorov-Smirnov statistics that are a measure of differences of distributions. We do see that the differences are larger across countries than within countries, but still there's a lot of variation both within countries and across countries. So these distributions are really, really very, very different. And most importantly, there is no very easy parameterization to really capture a large share of this distribution. So here we tried many different, perhaps customary or not really customary parameterizations of this distribution. It turns out that none of the distributions you might think of is actually a fit for a large share of all these distributions. So there is not one parametric family that is well enough suited to really get all the variation that we observe in this true heterogeneity of firms. So it makes sense in our sense to really go for the non-parametric way and not to constrain ex ante the role of technology in our paper, where we actually want to understand the role of technology for international trade. So we won't use any of these parameterizations because they are really not too good. In particular, those that we typically use. Pareto is the particularly worst of all the distributions here. So only around 8% of the distributions could actually be parameterized by a Pareto distribution. So that's not a lot. So I think it makes sense to really go for the non-parametric way here. Now, what will we do to understand it? In the beginning, I introduced a small toy example of what one could do. One could vary the scale, one could vary location, and all these different things. So what we will do is we will kind of use our model as a laboratory and understand exactly if we change stuff here in the model, and in particular, if we change the technology, the productivity distributions, what does happen to international trade flows, because this will really allow us to understand, how to understand this big question. So how does technology and trade interact? And what we will do is exactly two experiments that are the same as we did in the very beginning. So we will look at the first order effects, like really what is the Ricardian component? So where is Ricardo in Melitz and how big is it? So how much does it matter for international trade flows to understand where the technology, the distribution of these countries and sectors are relatively to all the other determinants of international trade that are captured in that model. The second thing we want to look at is the gradient effect. So we want to understand that how do different changes in fundamentals of the model, so for instance, changes in trade policy, how do they play out in this model? And then later on, we will test this in the data. And now I think I come back to the question that Robert asked in the beginning. So what do we actually want to measure? What do we keep constant? Because I mean, like by changing the distributions and by doing any changes and experiments in our lab, clearly we do to some extent also differ. Like we have to understand what will actually differ across these different experiments to understand how to interpret these information. So what we try to get is to really get at the Ricardian component. So we want to understand, or we want to get rid of comparative advantage to understand the role of comparative advantage. So we really want to find Ricardo and how important is Ricardo in our workhorse trade model. So that's kind of what we want to do. Now, how do we do that? Well, comparative advantage by definition in our world is revealed by autarky prices. So a country, like if you would look hypothetically at the autarky prices in a given country across sectors, you would see that the comparative advantage in a country has, is given by its autarky prices across different sectors vis-a-vis all the other countries and their relative autarky prices. So if you know the autarky prices of different countries and different sectors, that allows you to predict how trade flows would flow in that economy. So we try to do that. Clearly, we do not have only one price because we have this whole firm level heterogeneity. So what we will do is we will use CES autarky price indices, so this sector level price indices, and we take a reference country, so we will use every country as a reference country once, but like in a given run, a given experiment, we take one reference country, we take its CES autarky price indices across sectors, and shift the distributions of all the other sectors and countries in a way that every country has exactly the same relative sector level CES autarky prices. But at the same time, we do ensure that the country by price index remains the same as in the benchmark. So we do not kind of make China as productive as Germany. No, we want to make the Chinese car sector relative to the Chinese textile sector in a relatively being as different as the German car sector and the German textile sector, but we do not change the whole distributions towards each other. So I hope this becomes clear. And by this, we really modify and get rid of comparative advantage, really the Ricardian component. And this is also very, very much related to the paper by Costino, Donaldson, and Comuncher, where they tried to understand the role of technology in a Ricardian world in a parametric way. So there they did something that is kind of similar to this. Now, gets to our results. So what is actually the first order effect of technology on international trade? So here we see what happens if we eliminate modified comparative advantage in this model relative to changing anything else in the model. So changing symmetrizing country size or taking out symmetrizing trade costs and symmetrizing input-output linkages and all these other things. So if we take out all the other variation across countries, or relatively, if we take out this comparative advantage component, how much of trade flows are, or how much of the variation in trade flows is actually explained by comparative advantage alone. And we do see that clearly, so this is clearly bounded between 0 and 1. And in our version of the Melitz model with the empirical distribution, we see that on average, 43% of the variation in trade flows is explained by comparative advantage. So Ricardo technology plays a big role for international trade, as you might have expected, but we didn't have a number. So we really see that basically in almost all sectors, it's the single most important component in determining the trade pattern of trade that we do observe. And we also do see what we expected in the beginning. If we would go the standard way and use some parameterization, we would clearly, by artificially constrain the role technology can actually play, because the role of technology could not be as rich as it actually is in our models if we would use this Pareto assumption. And we see this here. If we would assume and if we would enforce this model, the microdata to follow Pareto distributions, we would only get a contribution of technology of 15%. So by assuming some parametric distribution, we would definitely strongly constrain the role of technology for international trade. So when it comes to the gradient effect, what we want to understand here is we clearly see that if we change trade policy, if we change trade costs in this model in our laboratories, we do see that there's a lot of heterogeneous effects. So there's clearly non-constant trade elasticities, and in particular, we do see that it depends a lot on how sensitive trade flows are to a given trade shock. So it's always 20% change in trade cost that I'm plotting here. So how sensitive a given country sector is, or a given country sector pair is to a change in trade flows, depends a lot on its trade share quantile in the outset. Meaning that here at the 10th quantile, we have countries that do already trade quite a lot with each other. If we change trade policy here by 20%, reduce it by 20%, the effect is substantially smaller, up to 3 times or 4 times smaller even, compared to countries that do not trade a lot with each other. If we would assume Pareto, that we do know Pareto and Melitz gives us constant trade elasticities, we do see that the response is flat across this dimension. So this is something that comes out of our model with the empirical productivity distributions and this from the Pareto distributions. And now this is particularly nice. This is something in contrast to the technology changes that we do not really observe in the real world. This is something that we can observe in the real world. We can see how do actually trade flows change and how does it depend on this trade share quantile in the outset, and see how this looks like. And this is what we want to do now. We want to look at the data and understand how do trade shares respond to, for instance, tariff changes, and plot it also across these quantiles. So this is now really an out of sample check. This has nothing to do with our models, purely looking at data. We do see that trade elasticities, the response of trade flows to trade changes in trade costs, really does vary in a way that is very, very, very similar to what our models predicts correctly specified. Here we can also do the same with distance elasticities, which we can also rank like this, which is also something that's very much in line with what our correctly specified model gives us. Yeah, and that's kind of my talk. I hope I've convinced you that we tried to answer the question, how important is actually technology for international trade? A question that we did not really know an answer to, and we can show that through the lens of our workhorse trade models, comparative advantage, so Ricardo, the classic old Ricardian component of technology, really explains 43% of the variation in trade flows in this model. And we also see that customary parameterization would drastically underestimate the effect. It is perhaps not surprisingly that constraining that role of technology, we do underestimate this effect. But what is also very, very important, what we see in this last graph, the gradient effect, is that technology does not only measure this comparative advantage. It's not only the Ricardian component that makes one country more productive than the other country, and this explains trade flows. No, technology is more. Technology is the backbone of our model. Technology governs how primitives of the model, in particular trade policy, affect international trade. So it's really also important, not only quantitatively, but also qualitatively. It's really important to understand how the model actually plays out, to understand how the mechanisms in the model work. And we do see that this is important. We see that the effects are heterogeneous across trade shares. We do see that a lot of variation gets lost by these parametric assumptions. So yeah, this is very important, but also what is very nice about this exercise is that we can use it to kind of compare it a bit to data. And we do see that macro data on responses of trade flows to tariff changes and distance elasticities do confirm exactly the pattern that is implied by our model fed with non-parametric productivity distributions. Okay, yeah, that's it from my side. Thank you very much for listening, and yeah, looking forward to your questions.
Okay, many thanks, Minnie. Very, very, very rich paper on 3 blocks. The first, the theoretical part, and the measuring part, and then this laboratory. What to do with the results then? Well, I can't see. Is there any question from the audience already, or not yet? Then I will start with the question, meaning from the whole setup of the thinking. So the Ricardian model in its textbook version is you have exogenous technology, and this shapes the trade patterns. So if my humble understanding of the paper is now basically you use the trade patterns to infer on the technology distributions and therefore also on technology, basically. So you a bit of revert the Ricardian assumption that technology is exogenous, it shapes the trade patterns, and you do it a bit reverse in a way that you have the market, which is the hardest reachable, and this basically determines your productivity distributions and maybe the levels then. So, well, or say it short, do you have some endogenous element in between how you measure it and how you interpret the Ricardian model then?
I would not say, I mean, I see what you mean. I mean, yeah, we do kind of use, we do use observations on like trade shares to different countries to infer our productivity distributions, but they are not endogenous. They are not endogenous in our model. So in our model, but also the assumption behind that we are kind of able to use something that is endogenous in our model, namely trade shares to different countries and also to the domestic markets. We use those observations to understand the underlying exogenous productivity distributions. So we do not kind of endogenize anything. So we do assume that productivity distributions are exogenous. What is endogenous in the model is which share of firms, and so which part of the productivity distributions matters for each given country pair. and their trade flows. And this information we use to infer the whole distributions, but these distributions are still exogenous. Does this partly answer your question?
Yeah, part. There was a paper by, I think, Harald Fadinger. He once also tried to re-infer on productivity from, well, industry level trade data, and he got a nice match, but I would have to think about that again. We have one question in the chat now, Oliver. Okay, so you're unmuted.
Yeah. Hello, thank you very much for a very interesting paper. I have two questions. How does the country sample affect your productivity estimates? Because you always take the most difficult market and then you infer the firm productivities from it. So if you would exclude, for example, the most difficult or the two most difficult markets, how would your productivities then change? Or otherwise, if you would extend your country sample, how would that affect the productivity estimates? And second question is, what's now the least bad productivity distribution? I mean, if we have a larger sample of countries in our trade model, I mean, we still have to use some sort of productivity distribution. So what's your recommendation on that?
So about the first one, I think this is an important point. So clearly, so we look at so everything we do here is first goes through the lens of a model, and it's also through the lens of a model that is calibrated to the set of countries and sectors that we do have. So this 43%, it's really like that's what, yeah, a comparative advantage explains in this particular set of countries, and this model through the lens of our model. The set of countries, I mean, so what we do, so we do model the rest of the world. So kind of to some extent, we do also try to take into account countries that are not in our sample in that, but this is clearly not perfect. So clearly, if we would have more data in more countries, that would for sure affect it. But I think this is important. So we have now increasingly, like we started with this idea and kind of had data like on this expertise to some countries, and then kind of increase the sample again. So in the end, the overall results are very robust. So that's, I think, important, but clearly, so like we try to take this into account by looking at the rest of the world and modeling the rest of the world. So it's not that we do completely ignore that countries also go to different countries. But yeah, within the model, that's the best way what we can do. The second question about like what should you do, and I think what I really want to bring across is like this paper is not about like, okay, look, Pareto is not good enough, don't use Pareto, and that's it. So so this is not what this paper is about. It's not about like criticizing Pareto, even though I see that sometimes this comes across as the main idea of that paper. The paper is about like really want to understand what is the role of management in international trade. And I think to answer that question, we need to really let technology play its role in the model. So I think for that context, it's really important to do that. Does this mean that we cannot take assumptions that are very, very convenient? I do not think it always depends on the context. I mean, I think that there's no one way to answer certain questions. But I think what is important and what I take out of this, like working a lot with this model and understanding, so I've learned really a lot about like the mechanics of the model on working with that. And I think we simply have to be aware of what we buy with this assumption. So what is actually the consequence of taking certain assumptions? Trying to take these assumptions, but one has to know that it's not only a mere, okay, you change your kind of some like effect size a bit, and that's so it might actually in the end have qualitative important results, and you might be you should perhaps be aware that a Pareto assumption with, for instance, if you look at policy changes, that it generates constant trade elasticities, and this might have very strong effect depending on what country pairs you look at, and you might know or want to know that you tend to overestimate perhaps the effect for countries that already trade a lot with each other, and you might underestimate the effect for countries that actually do not trade a lot with each other. So kind of taking some of these things might be important.
Okay, with another question first by Nina and then by Ruben. So Nina, please.
So yeah.
Do you hear me?
Yes, we hear you.
That's very good. Well, just one question, like about the estimation of productivity. I was just wondering whether you have a thought to use Cobb-Douglas production function and estimate technology as a residual of a Cobb-Douglas production function using some of the available methods like Wooldridge approach or Levison and Petrin approach. Although I understood, maybe I got it wrong from the presentation, that much of the firm sales is missing in Orbis data, right? So I don't know if that may have been an issue or something.
So actually, this is exactly what we did in the beginning. So when we started this project, we did kind of want to do that, and we did exactly. So if you look at the current version of the paper that is available, there's a working paper version available of the paper from last year, where we do exactly that. So where we basically use the Acrobat case and tracer methodology to estimate the productivity. But what we then we kind of presented the paper and discussed with a lot of people, and we realized that, I mean, clearly we take certain assumptions because we do not. So we always only have the Orbis data. So we only observed, and we do actually have good data. It's like the problem is less the representativeness, and we do have sales data for many countries, but we do not have quantities. We also only see revenues, and we have revenues, and we have a model here that has assumed CES. And if we have a model that assumes CES here in our calibration, then we cannot take revenues to infer quantities, because we do not observe firm level prices, we do not observe the quantities, then it's inconsistent, then we cannot estimate. So we cannot take revenues under a CES assumption as a good proxy for quantities, which is what we have done. And this is simply not consistent with that model. And that's kind of what people criticize, because like we made a big fuss about kind of really want to measuring everything right, but then taking an assumption in estimation that is actually completely inconsistent with assumptions of our models. And I think this is a very, very fair criticism. And that's why we bent back and really thought deeply and really worked really now a year on kind of trying to improve on that. And that's exactly why we came up with this novel methodology, because yeah, the other methods that are there simply would not work in a consistent way for our particular context. Yeah.
Thank you very much, and for the presentation as well.
Thank you for your question.
So with Ruben.
Okay.
Yes.
Hi. Thank you very much for the presentation. It was really interesting. If I could go back to the previous question just quickly, there is actually a way to consistently estimate productivity in line with the model. If you like, Klette and Grudikus have a method developed in 1996. There's a paper on that where you allow for revenue production function estimation. De Lucker has also implemented that. But that was not my question. My question was actually regarding the empirical productivity distribution and how you estimate it. Because how you estimate it non-parametrically, because my experience with using non-parametric estimation procedures for that is that it's very difficult given the nature of the data, and that there are several ways of doing it. And the several ways of using non-parametric estimates can change a lot the range of the estimates that you receive. And if you would use something that is approximately correct, my idea is that actually if you impose parametric distributions with a very heavy tail, so a Pareto tail, you would actually overestimate relative to the empirical distribution. And if you would have distributions with a very light tail, such as a log normal or a Weibull, you would underestimate relative to the empirical distribution. While here you seem to infer that the empirical distribution seems to be larger relative to all parametric distributions. And I wonder how you estimate this, and how does it come that all parametric distributions seem to underestimate the effects?
I think so. We do not. So the only benchmark we have here for this effect, that's really only Pareto. So like this, so this thing here, where we compare to that, we kind of have this effect of 43% in the empirical case, and Pareto case 15%, that we overestimate, that kind of we have a large effect of technology. That kind of comes from a comparison of Pareto. So we did not do that same comparison with parameterizing in any of the other ways. So that's important, perhaps to understand your question. But the question is important. So how do we do the non-parametric version. So we use the methods by Lee and Racine of like kernel density estimations. And it's actually, we tried different ways of bandwidth determination and kind of have like several robustness checks and kind of using that. And that seems to be quite, so that, yeah, that works actually quite well in our context. So I think
you estimate that on heavy tail data then, because you have very little observations in your right tail where you get very large data, and then you have a lot of variance there with non-parametric estimation procedures.
I think what we do in the end, I mean, like to implement that, we get these distributions on a grid, right? So we kind of estimate or we take a grid of the productivity we observe and estimate kind of the relative densities there. And yeah, we've used that in many variations. So it's given by so it is true that sometimes we have kind of only, so we also weight the data. So we do weight the data by like this inverse propensity method. So I think that's also probably important for this methodology. So we do put in weights kind of to take into account that we have different missingness in different parts of the data. So that's something that we do take into account. So we do a inverse propensity weighted kernel density estimation on the one hand, and and then we estimate for each grid of that we have this density, and we checked really like with very different. So we varied grid size in all dimensions you could imagine, and it seemed very consistent in a way. And perhaps one other thing about the overestimation part, you said, like, I mean, it's true that clearly the effect you get in these models, like on heavy, like it's a distribution with heavy tails or less heavy tails, and so on and so on. This is important, but here it's not about the trade flows, like of a single trade flow. It's not about the sensitivity of trade flows, but this is really the contribution, the variance contribution of technology, the whole distribution on explaining trade patterns. I think this is a bit, I mean, clearly this is not unrelated to what you said, but I think it's not one-to-one driven by what you just mentioned.
Okay, thanks.
Thank you.
Okay, thank you. There was in the chat a question by Mahdi.
I'm trying to see the chat.
No, I can read for you. I mean, he's he likes it very much, of course, the paper. And he basically asked whether there's also, basically you focused on manufacturing, and he would know whether this is also possible to do for services trade. I mean, it should be, because you basically need trade share data, so to say, right?
Yeah, good point. I mean, like the question is, so in the beginning, yeah. So in the beginning, when we started this project, it was like, as I said before, we kind of started with this classic TFP estimation, and then that's kind of clearly aimed at being used for manufacturing data, and that's kind of how we stick to that one. It's true that perhaps now we would be more flexible to also look into services. Actually, a good point. I've actually not thought about the fact that we would now also be, perhaps should be able to look at services. I mean, I've not really worked too much with the services trade data, so I don't know how, if we get all this information, like also about the exporter share in the services sector, like these data that we need to kind of recover the distributions. I've never, so it might be that they are there, I don't know. But if these data were available, actually a good point, then we should perhaps would have a possibility to also look into services parts. That's actually a good point. I'll think about that.
Might be interesting, because productivity data on services industries are very poor, basically. So it might be interesting to compare them in a way. There's no other hands raised or no other question in the chat. So maybe let me ask a last question. Do you think your results allow to compare, say, Chinese productivity levels or distributions to German ones? Meaning, in the charts you have shown on the distributions, we've seen China very much on the left, and it has been the Central East European countries on the right, and we have seen the more advanced countries in a way. So that's basically, it fits the expectations I would have some simple, well, GDP per capita data or productivity data from industry level analysis. But in the way you do it and you derive it, is basically, say you have on some countries are assembler, and just doing assembly of final products and have a wider sale, say to wider markets. Whereas in other countries, very specialized in high technology, might sell it just across the border because it's quite a different production structures they have in a way. And you compare, say, the Chinese assembly pattern of trade to more kind of high-tech products trade in a way. So
yeah, I mean, for sure.
Any ideas on that?
Yeah, I think this is an important point. So clearly, like, perhaps it's better here for the manufacture of electrical equipment. So clearly, like, our sector definitions are relatively rough. So there's, as you said, like a lot of different things in here. And this is kind of something that is captured also in here. So part of these differences that we kind of see China here to the left of countries here might be due to the fact that there's a different composition of types of like what subcategories of the sectors are in there. I completely agree. Yeah, that's part of that. I actually do not. I wonder if it's like how big of a problem it is. I'm not sure. I mean, it's for sure the case that this is that this is part of what is captured here. Completely agree. But still, on the other hand, if I look at the trade data, I mean, like we do. Then, I mean, we derive, like, when positioning these distributions relative to each other, we use actual trade data or like actually domestic shares. So to some extent, this is taken into account. And this, I mean, so it does for sure not allow to look into the details of these assembly lines and what part, like, yeah, because we do in the model not differentiate between different kinds of products within sectors. So that's something that we cannot look at because of the design of the model. So my answer would be, I think you're absolutely right. This is part of what drives these differences. And I think one thing I want to do at some point when I already have and spent so incredibly many hours in deriving the distributions, I really want to understand them better. Like what kind of actually underlies these distributions? What explains them? What explains differences across sectors within countries and also across countries? So is there institutional and so on and so on? What's stuff that is kind of explaining it? And this is for sure, I'm very sure, and a very important part of it. But I do not know if it would, in a model that does not speak to, like, because everything we say is anyways through the lens of this model, and this model is of course not the world. But yeah, I do not know if I believe that it affects our makes the interpretation of our results through the lens of the model more difficult. I'm not sure. Do you have a specific concern there?
I think I have to read the paper more carefully if I flag that. But I just wanted to flag that, for example, for China, the standard argument would be China's assembly. So basically, it's all the products are going there, and the Chinese assembly lines are very labor intensive, and therefore they have a low labor productivity in a way. Basically reflected in your data as well, in a sense, right?
Yeah, no, I'm absolutely completely sure. Like this is for sure part that drives this difference. I'm completely
exactly. The question is a bit what we talk about technology versus productivity or labor productivity. So I think that's the gist of my question in a way, right?
No, okay, I see that's an important point. Yeah. So when we talk here, when we say technology. No, a very important point. When we say technology, in this context, we talk about productivity distributions. We do allow in the model for differences in production. So we have this input-output linkages and like how much material inputs is used from each other sector and what's the value added and labor input and so on and so on. And this is allowed to vary across countries in the model. Right. So that's kind of allowed to vary, but like all of it is a Cobb-Douglas production function. But the parameters are allowed to vary across countries and sectors. So to some extent, that's in there. What is also in there that kind of these differences that you're talking about are captured in what we call productivity. And yeah, I mean, like what is productivity to start with? Yeah, I think part of it is clearly that the different products are like I think productivity is something that is a multidimensional object to some extent, and we force it here to be on one, on one line in one dimension, which we call phi, right? And I think one of the dimensions is for sure the one you mentioned, and we artificially map that dimension onto this phi dimension here, for sure. That's clear. Yeah, that's an important part of it, and I'm very sure that this explains part of these differences. But I do not think that it necessarily it's still an important component that explains why China, like in this context of the model, still explains why China has a very particular trade pattern compared to another country like Germany that has a different distribution of relativity, but it does not open this black box of these dimensions of relativity. So here I completely agree. So we cannot say anything there.
Okay, thanks. Maybe one last clarifying question from Mahdi from the chat. Basically, whether you interpret the results having estimated labor productivity or total factor productivity, then I think. So that what we estimate as productivity?
It's total factor productivity.
It's total factor productivity. So okay, because then you have all the capital and and also industry.
So what you see here. Yeah.
Right. Okay. Okay, great. So then let me thank for this very interesting presentation and the good discussion. Looking forward to get the final, or at least the next version of the paper.
Hopefully the final, you never know.
Hopefully the final one.
I'm also looking forward to the moment I finally can say this.
And as I said, once the paper is finished, we are happy to post it on our website as well, and participants can download probably from your website or from us as well.
Yeah, thank you very, very much. And thanks for the very interesting question and also the very interesting comments. In particular, the services part, I'll definitely think about it. I think that's a very, very good comment. Thank you very much.